Okay, so today I think is more sort of light fun, I hope, for you guys. More applications of the Baire category theorem. In particular, we're going to start off with an application of the important closed graph theorem. Okay, so what we're going to do is show that, in fact, the set of continuous functions whose Fourier series diverge on a dense subset of negative pi comma pi is generic. Okay, so if you were in the Fourier series class, if you're in the Fourier analysis class, actually none of you were except maybe Eric. You weren't, but maybe you were sitting in on it, weren't you?
No.
Okay, so you probably saw at one point we constructed a Fourier series which diverged, I think, on a dense subset. And this is to say that in fact that's that sort of phenomenon is generic. Okay, so just to review some basic ideas again. So B is going to denote the continuous functions on negative pi pi. This is going to denote the sup norm, so the sup of f of x as x ranges over negative pi pi. And then f hat n is the nth Fourier coefficient. So you integrate f of x against e to the negative pi of x, and you take over the interval negative pi pi, and you take you introduce this normalizing constant. So this is the Fourier coefficient, and then you have this thing fn e to the negative e to the I in x, which is the Fourier series associated with f. So Fourier series of f. Okay, and just a notation. S of n is going to denote the, so this goes over all integers n, and S of n f is going to denote the partial sum of that from negative n to positive n. This guy's the partial sum. Okay, and turns out that that S of n can be realized. S of n can be realized as f convolved with a function called the Dirichlet kernel. So dnx is summation dinx from negative n, and that turns out to have a closed form expression, n plus a half x over sine x. Okay. So, and this convolution is on the interval. So when we say convolution today, what we mean is that we're taking the convolution on negative pi pi. So f over pi should be x minus 1 dy, which by changing variable, we could also write as f of x minus y dy minus 1. So this is just the background notation for Fourier series. This thing called the Dirichlet kernel, if you've seen it before, it unfortunately is not a good kernel for reasons that we'll see shortly. So you can't just hope that you can recover your function by letting n go to infinity. If it were a good kernel, then as long as your function were continuous, then this would recover your function. So it would recover your function very, very simply, but that's not the case. It's not. Okay. So the main, one of the two big results we're going to get today is the following: that, like I said earlier, that continuous functions whose Fourier series diverge on a dense subset of negative pi pi are in fact generic. So here's the statement: given any point in negative pi pi, there exists a continuous function whose Fourier series diverges at that point. There exists a continuous function whose Fourier series diverges at that point. And second, the set of continuous functions whose Fourier series diverge on a dense subset of negative pi pi is generic. Okay, and so here's the strategy. We're going to prove this by contradiction. So and the loss of generality, let's assume that x naught is 0. And the strategy is going to be this. Let's define let L sub n be a linear functional. Let L sub n be a linear functional in the space. And it's going to be given by Lnf is going to be the nth partial sum of the Fourier series of f evaluated at 0. The nth partial sum of the Fourier series of f evaluated at 0. Recall that S of n is f convolved with d sub n. So this is going to be f negative y dn y. So we create this linear functional, and what we're going to see is that L sub n, each L sub n is continuous. Okay, with some bound that will denote a capital L sub n. Okay. 2, we'll see that these bounds actually go to infinity as n goes to infinity. So let's think about how this goes. Well, let's suppose that that at 0 there is no continuous function whose Fourier series diverges, right? In other words, given any continuous function, the Fourier series is going to converge. Okay. If the Fourier series if for every f our Fourier series converges, that means that if 1 is false, so suppose 1 is false, then, right, the Fourier series for every f converges. right? So that means that L and F is finite for all F in our space. Right? L and F is finite for every F in our space. Right? And further, that's going to happen. That's going to happen for every n. Right? For each fixed n, this is true. So what we have is pointwise boundedness. We have pointwise, that is to say, function-wise boundedness of the L sub n on the Banach space B. Right? So by uniform boundedness principle, by Banach-Steinhaus, that tells you that you have uniform bound of the norm, right? That the supremum over all n's of the norms of these guys would have to be finite also. You have a uniform bound. Pointwise boundedness leads to uniform boundedness of everybody in your collection, right? But that contradicts number 2, because we just said that the norm goes to infinity. So this is the overall strategy. We create the state, the partial sum, the nth partial sum valued at 0. It'll be easy to see that it's in both cases sort of an easy calculation to see that 1 is continuous and 2 the bound goes to infinity, and then you run into a contradiction with Banach-Steinhaus. So that causes one to be true. Okay, so let's do it. It's pretty straightforward. So lemma. Let's prove this one. The L sub n are continuous. Okay. So proof. It's pretty straightforward. Say, well, look. Let's look at L and as a function. Right. Well, by definition, that's going to be 1 over 2 pi, that's the integral from over pi of f negative y e and y1, right? Which is right. This is completely obvious, right? You have 1 over 2 pi, you can pull by the triangle inequality, you have this. You have this. You can pull this out, right, because you get the norm, you get the sup norm, 1 over 2 pi times the sup norm, right, times this 1 over 2 pi integral v. Okay, and so this thing is finite. We're going to call this thing. This thing is actually going to be our bound L sub n. So right now, what we've just shown is that the L sub n, each of the L sub n is continuous. Each of the L sub n is continuous, and what we're seeing right now is that the operator norm of L sub n is less than or equal to this number. L sub n, capital L sub n. So let's. So L sub n is defined to be this L1 norm of P. Okay, so maybe I should write it like this. So the L sub n are continuous with the norm of L sub n equaling L sub n, which we define to be this 1 over 2 pi negative pi, the L sub value of D. Okay, so that part is easy, and then the second half of this right now we've shown that the norm is less than or equal to this. We want to show that the norm actually is equal to this. So part 2, let's see that also actually is greater than or equal to that number. If we let G denote the sign of dx, and we apply well, L sub n is this thing, but you recognize that as little l and apply to G. Right, using the fact that dn is an even function. So you just take d against its sign, right? D against its sign is of course the absolute value of d sub n. Right. So right. So that's not enough, right? So that if this were a continuous function, then we'd be done, right? If this were a continuous function, then we'd say, okay, well then the norm of G is 1. The norm of G is 1, and we see that the size of G equals L sub n times the norm of G, times the suit norm of G. Right? So that would tell you that we actually do attain the value of L sub n. Okay. But G is not in our space, right? G is not in this G is not a member of B. So we can't. This doesn't do it for us immediately. Right? Right. Okay. So what you do, of course, is you create create a sequence as the king of continuous functions of norm all less than or equal to 1, such that S of k converges to G in L1. You have some measurable, this is a measurable, G is some measurable function, and you approximate with continuous functions in L1. Okay. So, okay. Then, if we look at ln fk, right, that's going to be 1 over 2 pi pi k negative y what you see, or actually let me look at ln fk minus ln g. We're going to get this. We get this, and this is a continuous function, so it's continuous function on negative pi pi, and so it has some bound, right? So this, right, is controlled by this. This is less than some constant, right? And so you get some constant times something that goes to 0 because the fk converges to g in L1. So nothing constant. So this thing goes to 0, right? And that tells you that Ln, right? So the Ln fk tend towards L sub n, which tells you that the soup of that tells you that the norm must be greater than capital L sub n. Okay, everyone okay? I think there's nothing controversial. There's nothing controversial. First, I was thinking maybe one had to use dominated convergence to do this, but it's not dominated convergence. And then I thought maybe one had to use it using that Dn is a good kernel, but Dn is actually not a good kernel. And then I realized it's actually trivial. Okay, so last part. Right now we've shown that each of the little L sub n's is a bounded, is a continuous linear functional, and we know what the bound looks like. It's the L1 norm of the Dirichlet kernel. So now the only thing we can do is show that these L1 norms of the Dirichlet kernels actually go off to infinity. And we'll do it using this one, that there exists some constant such that L sub n is greater than or equal to C log n. And once you have that, of course, then we're done. Okay. And this turns out to be just a calculation. Say, okay, well, Ln, right, that's the integral. That's the L1 norm of the d sub n's. But we use the closed form expression for the d sub n's. So this is it's going to be greater than or equal to some constant from 0 to pi. Again, we're using the evenness of d. Sine n plus 1/2 y over y dy. Then using chain of variables, we get that some other constant sin x over x dx. We let x be n plus 1/2 y. The constant is a different constant. Okay. And then we're going to change this into a sum. So this will be the sum from k equals 0 to n minus 1 of the integral from k pi to k plus 1 pi of And then we do sort of the simple bound, k equals 0 to n minus 1, 1 over k plus 1 pi, the integral k pi of k plus 1 pi, sin x dx. Because you're dividing by the biggest value of x, right? You divide by the biggest value of x, that's going to be smaller than dividing by x. Which is equal to k from 0 to n minus 1, 1 over k plus 1 pi, as the integral from 0 to pi using periodicity of sine. This is going to be some constant, right? This is just some constant. Right, which gives us something like c log n. Right, because we're summing the harmonic series. So that gives you the first thing, that you can create. You know that there's got to be a continuous function whose Fourier series diverges at that point, at whatever point you've chosen. The second part follows from the first. So part 2. So right. So we know, we've just seen from what we just saw, we know the set of continuous functions for which the supreme of SNF at 0 is finite over all n must be of first category. Is that clear? Let me think about it for a second. A set of continuous functions for which what we just saw blanking out this again. What we just saw was that yeah, that's right. Right? Because if it was a second category, right? If it was a second category, then Banach-Steinhaus would say that you got the uniform norm. You have the uniform norm. Right? Yeah, that's right. So right, if it's a second category, if it's a second category, right? If it's a second category, then uniform boundedness would imply that, remember, each of these guys is the also Banach, right? Would imply that the also Banachs are all uniformly bounded. Right? Would imply that those guys are uniformly bounded, and that leads to the contradiction. Right? Right. So in the first part, we said that we were saying that it can't be empty, right? But really, we can say something a bit stronger, right? And that is that it must be of the first category. Remember, there were two forms of the Banach-Steinhaus, and the second one involved the set of points on which you have pointwise boundedness being of second category. Okay, so if it's a second category, you end up with this contradiction. So this set must be a first category. So what that tells you is that the set of functions, the set of continuous functions whose Fourier series diverge at 0, whose Fourier series diverge at 0, must be of the first category. Convergence. Right? Because if the Fourier series converges at 0, then the suit is going to be finite. Okay. So the set of continuous functions whose Fourier series converge at 0 must be the first category, and those who diverge at 0 must be generic. Let's do the complement of that. The set of continuous functions whose Fourier series diverge at 0 must be generic. Okay. Then, given any countable collection of points x1, x2, etc., the set of functions whose Fourier series converge at any such point is of first category. Right? Because it will be a union of sets of the first category. Right? If you converge at one of those points, that's a set of first category. Then the guys who converge at any one of those points is the union of all those. It's the countable union of those guys. And so, being a union of sets of first category. And so, the set of functions whose Fourier series diverge at all points, all such points, all of those points is generic. It's a complement of the set of the set of first category. So you can make up, whatever, you can choose a dense subset of negative pi, and it will, that the set of functions that diverge, this Fourier series diverge on that chosen set is generic. Okay, so that's the first application we'll see for today. And the second one will be the open mapping theorem. More traditional topic for functional analysis. So we have T going from X to Y, a mapping between Banach spaces. So you have these Banach spaces, and the definition, what we mean by open mapping. If for all open sets E contain X, the image T is an open set in Y, then we say T is an open mapping. Something you may have seen, you've probably seen before, is that if you have any function going from one topological space, I'm sorry, if you have any function going from a Banach space to another Banach space, then it is continuous. It's continuous if and only if for all open sets E, the pullback of E through F is open. So E in Y, the pullback is open in X. I don't know, how many of you have seen this before? Have you seen this before? You should. Okay, if you haven't, just work it out. It's an easy metric space exercise. Okay, so this is true for metric spaces. Okay, so so here we have the let's go to the statement of the theorem. So you get T 1 a continuous linear mapping, so linear transformation. If T is surjective, then that T is open. So the continuous linear transformation, if you know it maps onto, if it maps onto the space, then it must be an open map. Okay, so notation. When we write B sub x, x comma r, we mean the ball in x, centered at x of radius r. Ball in x, center little x, radius little r. If we write bx1, we mean bx0, 1. That's the ball centered, ball of radius 1, sorry, I should have R here. Ball of radius r centered at the origin. So these are just abbreviations that it's fine, it's easy. Okay, so let's go. Since T is linear, it suffices to show that that T bx1, if you look at the image of the unit ball, it contains. So if you look at the image of a ball centered at the origin, it contains an open ball centered at the origin. Right. Because by linearity, you can scale this, and by linearity you can shift it, you can translate it around. Right. So if you know this is true, then given any open set, you just take a point inside there, and you take a point inside there, and you see that that the image of that point is interior to the image of T on that set. Right. So any interior point gets mapped to another interior point. In other words, the map preserves openness. So what we're doing here is showing that we're taking 0 as our interior point and showing that its image is still an interior point. An interior point to the image. Okay, so we're going to do this in 2 parts. First, we'll prove the weaker claim, weaker claim, which is that the closure of the ball, the closure of the image, contains an open ball centered at the origin. this is pretty cool. I hope you like it. We know that since T is surjective, the union of the images of the balls of radius n centered at the origin is the whole target space. Right? Oops. Right, because you take the balls in x, let's say that over here is x and over here is y, right? You take the balls of increasing radii, right? And eventually you're going to cover the whole space, right? So the union of the images of these guys is going to cover the whole space over here. Right? Because T is surjective. Okay. So we have this cover. Of Y, which is a Banach space, and so we know that by Baire, we know that one of the Tx, one of these images is not nowhere x. That is, its closure as a non-empty interior. Okay, but you know that T is linear, right? So this Tbxn is just a scaling of Tbx1, right? T is linear, so this guy here, right, is the same thing as Tbx1 scaled, right? Scaled as some constant, right? And so really, if we know that one of these guys has a non-empty interior, we know that all of them have non-empty interiors. Okay. So in particular, by linearity, we know that Tbx1 contains some ball centered at some point and of some radius. Okay. Okay. So right. So here's the y space. Here's the x space. Here is bx1, origin, radius 1. And there's some image over here, and it contains y naught radius, a ball centered at y naught and of radius epsilon. So, here's the picture. So, okay. So we, in particular, we know there exists some point x1 in that ball. So there's got to be some point x1 in here that gets close to this y naught, right? Because this thing is contained in the closure of the image of this, right? So we know that there's got to be some point here. We can make, given any point in the closure of the image, we can find some guy here that's arbitrarily close to that guy, right? So we know that there's somebody there such that t of x1, which we will also call y1, t of x1 is very close to y naught. So this guy is less than epsilon over 2. Okay. consider the ball Vy epsilon over 2. Given any y in there, what we're going to see is that this ball is contained inside that this ball is interior to the image, to that closed image. So we'll see that Vy epsilon over 2 is actually contained in TVxy. So pick any point in there. Pick any point in this thing. We know that y minus y1 is contained in T of Vx1 bar. Remember what these things are. This y1 was your Tx1. Tx1 is the guy who is within epsilon 2. Right. Tx1 is the guy who is in the epsilon over 2 ball. Right. Okay. This may look a little bit mysterious, but let me see if I can clear it up. Okay. So.
Do you want a point y in the ball in y centered at y0?
No, you don't actually. Yeah. So this. Okay. So let me explain what's going on here. Let me see if I can explain what's going on here. Okay. So x1 is in Bx1, right? That tells us also that negative x1 is in Bx1, right? Then t of negative x1, right? That's the same, negative Tx1 is also in Bx1. Right? So now you're taking, oh, wait a second. Maybe I can't. Maybe I'm wrong. No, we're good. What? Wait. So, let me look at this. So if we had y1 plus y, right? If we were y1 plus y, that's good, right? Because y1, right? We got this thing. Let me blow up this thing here. Y naught epsilon, radius epsilon over 2, and y1 is inside here. tx1. y1 is inside here, right? And if you're adding on somebody of size epsilon over 2, then that's still going to be inside. Right? y1 plus y is still going to be inside there. Right? I could also say y1 minus y is still going to be inside there. Right? Because you're subtracting off somebody of length epsilon over 2. It's the same as adding on somebody else of length epsilon over 2. Right? Okay, but we know that this set is symmetric. Right? So I can just as well say y minus y1. Certainly if I know that y1 minus y is in here, and y minus y1 is in here as well, right? Because the set is symmetric. Are you convinced? Did I convince you? Oh, good. Thanks. Okay. So so y minus y1 is actually in there, and then if we write so then y, which we realize as y1 plus y minus y1. Is contained in the closure of T dx2. Right? Because this guy is contained in T dx1 closure, and so is this guy. Right? They're both in the closure of T dx1. Right? And so their sum is going to be contained in the closure of T dx2, which is the sum of T dx1 and T dx1. So what does that give you? That gives you that I'm sorry. So this is not exactly right. There should be a 4 here, not 2. Okay. So what we just seen is that by epsilon over 2 is contained in T dx2's closure, and so by epsilon over 4 is contained in T dx1's closure. Okay. By the by epsilon over 4 is contained in T dx. Eric, you look bemused. What's wrong?
No.
It's just amusing. It's just amusing.
Yeah.
Okay. Okay, everyone all right? Everyone with me? Okay. So what we have right now is the weak claim that the closure of a ball, the closure of the image of the unit ball has an interior. I'm sorry. Contains the ball concentric at the origin. Okay. So remark, for convenience, let's take replace t by some constant, this constant times t. Then using that, then what we have is that t dx1 closure contains by rather than by epsilon over 4. Okay. And of course, dx to the minus k closure is going to contain dy to the So just let's just switch our operator slightly for ease of notation in what follows. So here's the claim. Now let's prove the actual claim that we want. That t dx1, the image of the unit ball, actually contains a ball centered at the origin. In fact, the ball of radius half. So this turns out to be pretty cool. Say, okay, well, let's pick some y in dy half. Pick some y in dy half. Right. By half we know is contained in the closure of the image of bx a half. Right? So we know we can get some x1 in bx a half such that the distance of tx1 minus y is smaller than, as small as we want. So let's say it's smaller than 1 over 4. Okay, and then you iterate. Say, well, iterate. There exists an x2. Well, let me say it like this. Notice that y minus tx1 is contained in the 1 over 4 ball in y. And now we iterate on this thing. Right? This thing is contained in the quarter ball, and so we know there's somebody in the quarter ball over here that approximates that guy to a degree of 1 over 8, right? And we keep on going. Right? So there exists somebody in the quarter ball, right? Such that y minus tx1 minus tx2 is smaller than 1 over 8. I.e. such that this thing is 1/8 ball in y. And you keep on going. Right? So you obtain one obtains a sequence x1, x2, blah, blah, such that each of the x of k's is contained in bx 1 over 2 to the k. And so the sum of these guys, right, converges to some x in the one ball. The sum of these guys converges because the space is complete to some x in the one ball, and since y minus the sum from 1 to k is contained in the 1 over 2 k plus 1 ball, we see by continuity of t that t of x equals 1. And so So y actually is in the image of the one ball, of t on the one ball. So that's the open mapping theorem. Let me put up some obvious corollaries. So corollary 1, if you have t a continuous linear functional, continuous linear transformation between Banach spaces. If t is bijective, then t inverse is continuous. Well, that's obvious, right? Because if t is bijective, then you have an inverse map. Right? But t being surjective means that t is open. Well, t being open means that t of any open set is open, which means that t inverse is continuous. Right? So it's an immediate consequence, right, of the fact that this guy is going to be continuous if and only if t is open. So the proof is this is continuous if and only if t is open. And we just showed that t being surjective makes it open. What that implies, and thus what you get is that there's a bound that t is bounded, right, and that t inverse is bounded, right? T inverse is bounded and t is bounded, right? So in other words, the norm of Tf is comparable to that, not just bounded above, but in fact comparable to that. That gives rise to the second simple corollary. If V is a vector space, and it's complete with respect to two norms, norm 1 and norm 2. If the identity map is bounded from norm 2 to norm 1, then the norms are equivalent. That is to say, comparable. Right? And the proof is what we're saying. This is saying that the identity map is bounded. So all we're doing is applying the previous corollary to the identity map. We have a continuous linear transformation from one Banach space to another. It's certainly bijective. Right? This is saying that it's a continuous, right? It's a linear transformation This means that it's continuous. So it's, it's clearly bijective. It's saying it's continuous, so we satisfy the conditions of the previous corollary. And so that tells you that the norm of one space, right, I, that the norm with respect to y is the norm once, the first norm is comparable to the second norm. So it's just applying the previous corollary to the identity. Okay. So that's it for the open mapping theorem. So next time we'll talk a little bit more about Fourier series, and then Anna, I think, will give the rest of the lecture for that day. I should have thought of this earlier and made each of you do a lecture. It was so much easier. But instead of the final or something. Yeah, and then the last class will be on Vesicovich sets. So I don't know if you've heard this term before. Actually, one of the Pomona's seniors is doing a thesis on Vesicovich sets. So Vesicovich sets basically has to do with something called the Kakeya needle problem, which is you have a needle of length 1. What is the smallest area set you need so that you can make that needle turn in all directions? Certainly, if you have a circle, you can rotate that needle in all directions, and you say, okay, I'm done, right? But what's the minimum size? What's the minimum area of a set that you need to sort of be able to back that needle up, turn it, and come back, like parallel parking, sort of, right? What is the smallest area you need to do this? This actually turns out to be related to a multiplier, Kairon-Segment multiplier problem, which is that if you take the Fourier transform, so it's called the disk multiplier problem. You have a function, you take its Fourier transform. You have a function on d-dimensional space. You take its Fourier transform, and then you chop off the Fourier transforms in a ball. Okay. So you say, okay, and then you take the inverse Fourier transform of that. On what LP is that bounded? Okay. This is a famous result of Charles Feckerman, that in fact it's only bounded on L2. So that operator is only bounded. This multiplier operator is only bounded on L2. And the proof actually uses